All right, so for problem 3 on this assignment, you're implementing saturating arithmetic. And there are two functions you have to write. The first one for two unsigned inputs, and the second one for two signed inputs. And what saturating arithmetic means, as the problem statement says, is if the sum will underflow or overflow, you return the maximum or minimum corresponding value for that type. So what I mean is, if we have two unsigned integers here, and you have an int max plus like 5 or something, then you don't return the overflow amount where it wraps around. You return int max because it will overflow otherwise. Similarly here, if you have like int max plus 5 again, you don't return the negative number that wraps around, since remember that the signed representation for integers has a wrapping around. So you will return the maximal value. And similarly, if you underflow, that is hit int min, you will return int min. Of course, it doesn't have to be integers here. They could be char, integer, floats. So your function has to work generically for all possible signed and unsigned types. To do that, the easiest way to figure out what to do is to look for patterns in the bits when things overflow or underflow. So what do I mean by that? Here I have made a small test file, and just has a few variables, and then ran it in GDB and put a breakpoint before I return. So I'll show you. So here I have 5 variables: signed integer 1, signed integer 2, unsigned integer 1, unsigned integer 2, and a float. And they're all 0 initially. And this is a pretty useful way to figure out what happens to the bit pattern. So for example, here, if I examine the bit pattern for SI1, it's all 0 as we expected. Similarly, for UI1, it's all 0. And then for float, it's all 0 as well. This is a denorm form, remember, from lecture and from lab 4. So here we can, the good thing about GDB is you can in real time manipulate these variable values and examine what happens to the bits. So let's try to set, let's do unsigned, UI1 equal to like 9, and then examine what UI1's bit pattern looks like. As expected, this is 1, so 2, 4, 8, so 8 plus 1, which is 9 as we expected. And then if we set UI2 to be 10, and if we examine the bit pattern, it's 1 more than the bit pattern for 9. And if we set one of these variables to be equal to the sum of both of them, like this, it's 19. And now we can examine what the sum looks like. So here, this is 19 as expected, 1, 2, then 4, 8, 16, so 16 plus 2 plus 1, which is 19, as we see here. So what now? Now we know that while it's not saturating, as in this is not becoming all ones, we're getting the correct result. So what happens if we hit the int max, in this case for unsigned? That case happens when it's all ones, right? So how do we make all the bits all ones? Well, there's a pretty simple way, because remember, if we set this back to 0, and we examine the bits, it's all zeros. And if we let this be equal to the bit negation, we can see that it's all ones. And so this number is int max in this case, where all the bits are ones. And now if we add 1 to it, so let's once again print this just to make sure. All right, this is int max. If we add 1 to this number, we get to 0. And this makes sense if you look at the binary numbers. So what happens when you add 1 to this string? Well, you'll try to add 1 here, becomes 0, carries a 1 over, adds, becomes 0, carries 1 over, and so on, until the very end where this bit becomes 0, carries a 1 over. But all this integer has is these 32 bits, right? So what happens is they'll all become 0, as we shall see here. So if we set this equal to this plus 1, and then examine the bits. As we expected, it's all zeros. So this is just a way to get you started to think about it. You can, try this on your own and check out what the pattern is. That should help you figure out how to write your function. So let's do the case for signed here. So here, check what the sign says, 0, and this is also 0. So let's set this one to be -10, and the other one to be positive 56. Why not? And then if we examine the bits, so this is 1 and it's 2. So 56 is not surprising. The only difference would be if, since this is positive, this first bit is 0 to indicate it's positive. This one might be a little bit counterintuitive if you don't remember what we talked about for unsigned integer representation. The number will wrap around. So what I mean by that, if I get to int max for a signed integer, what will happen is all these bits will become 1, where the first bit is still a 0. So how do you get to that? Well, good thing remember for our bit manipulation we learned in class, we can take a 1. So let's set si1 equal to 1. Then move this 1 over 31 bits. And now if we examine this, you have the 1 with all zeros. And to invert it, you just do the bit negation. And this is the signed int max. So if you examine the bit pattern, oops, let me clear this. It's all 1s and a 0 at the beginning, as we expected. So once again, to print the value, this is the signed int max. So now, what if we add 1 to this? What happens? Well, if you look at the bit pattern, what would happen is you add 1 to this bit becomes 0, moves 1 to here, becomes 0, moves 1, and so on until here becomes 0, add 1. So it will become 1 and then all zeros at the end. So what happens to that? Well, we got to int min, it seems like. So let's set this and then check the bit representation. So here you can see 1 and all zeros. So this is pretty interesting because if you think about it, if you represented negative numbers in the same way that positive numbers were represented, where this indicates it's negative and this is 0, so this would be -0, it doesn't let you really wrap around so much because what happens right now is you're going, you're adding from 0 all the way up to int max. Then if you add 1 again, you're circling down the number line to int min, which is here. So if you print si1 right now, this is int min, and if you add 1 to this, increments once. So what happens to this bit pattern? Well, if you examine it right now, you see that I add the bit pattern. This wraparound allows the bit pattern to move in a natural way, where I'm adding 1, so the first bit incremented by 1, and so that all the way until I get to -1, it's all 1 out on all the bits. So now if I add 1 to this, like what happened before for the unsigned int, all the bits should become 0, right? So if I go si1 equals si1 plus 1 becomes 0, and if you examine the bits, it's all 0. So this is pretty interesting because the negative number, the pattern is counterintuitive, right? So here I'm gonna let you work on your own, just digging around in GDB or however other way you want to, and figure out the pattern. And once you figure out the pattern, you'll know pretty well how to write the sine type function.